Okay, so welcome to my talk. I'm going to talk about processing in network, more specific about the programmable NIC in the context of RDMA and how we can do data process offloading to that programmable NIC. And this work, I work on this for quite a while, roughly a year, and I had support from Claude on the use case and also Khan, who did something similar beforehand, but not in the context of in-network processing. So, as I said, this is in the in the context of RDMA, and the adoption. RDMA gets more and more adopted for different use cases. I mean, originally it came in supercomputers, and there it is essentially the backbone. So high-performance networks are really the backbone of supercomputers. But we also see systems in rack scale architecture where we have like applications as the distributed main memory stores such as RAM Cloud or Farm, and also key value stores such as Pilaf, which take advantage of this low latency network interface. But this continues, and now we actually have RDMA over commodity networks such as Ethernet, and Microsoft, for instance, is deploying it at the data center scale. So we see there's really a lot of interest and growth around RDMA-based applications. So essentially my talk is going to be in 3 parts. First, I will say a little bit about RDMA and RoCE, and then about our programmable NIC, its architecture, its implementation, and then I present the use case, the distributed radix hash join, where we actually use that programmable NIC. So I guess some of you are familiar with the high-level semantics of RDMA. Essentially, there's different modes how you can use it. For instance, there are service types, so you can have like connection-oriented or datagram service, and connection-oriented you can imagine is similar to like a TCP connection, where you actually have a very specific remote and local node. So the 2 nodes participating in that connection are defined, and they build like a queue pair. And this is called queue pair in RDMA because you have like this send and receive queues in the NIC, or at least that's the abstraction. And you can also choose between reliable and unreliable service. So this is very similar to like TCP or UDP, where in the reliable case, you actually make sure that data that gets transmitted is arrived. And RoCE, which we are going to use, actually only supports the reliable case, and we also only care about connection-oriented service. Then there's also different command types. And there's 2-sided commands, which is send and receive. And there are 1-sided commands, which are read, write, and an atomic operation, fetch and add. And on the difference between them is essentially that in the 2-sided case, which we have here, the local node, for instance, would issue a send command. Then the local NIC will execute this. But then on the receiving side, the CPU also has to issue a receive command. And this is necessary because the location where the data has to be placed is not known a priori. This information is issued with that receive command. So only after the host issues this receive, the NIC will actually know where to place the data. And here in this example, this actually happens before the data arrives, which is the ideal case, but this could also happen later. And in that case, you actually need to buffer the data, which might lead to an additional copy. Then in the 1-sided case, here we have a write command from the local host, and then the NIC will essentially execute this. And since the write command actually contains the remote virtual address, the NIC on the remote side can immediately place the data, and that remote CPU is not involved at all in this transfer. And in general, this should have slightly layer overhead and not introduce any delay in case the remote CPU is actually not ready and hasn't issued any receive. But it has essentially the drawback that this memory location have to be known a priori, and usually this requires some kind of exchange in the beginning or regularly, where actually this information is exchanged among all the nodes. While I think most of you are kind of aware of this high-level semantics, I now want to go a little more deep, so you actually see how we later implement this on an FPGA. So essentially, RDMA and also RDMA over Converged Ethernet, they look very similar in the point of view from the protocol. So we have different layers. In the protocol here on the left, we have like Infiniband, first the physical layer. Then we have something called like a global routing header, which essentially specifies the nodes, like an address. And then we have Infiniband-based transport headers, and the plus indicates that there can be additional optional headers which are encapsulated in this base transport header. And on top, we have like payload, which is the raw data. And in RoCE v2, so RDMA over Converged Ethernet, where Converged Ethernet actually stands for data bridging Ethernet. And what it means is essentially this is more or less lossless, almost lossless Ethernet. And this is very similar to what you get on the Infiniband, which is also in theory almost lossless. And in RoCE v1, essentially we just change the physical layer. So we go from Infiniband fabric to Converged Ethernet. We keep the global routing header, which is actually the same format as an IPv6 header. And then the Infiniband protocol and payload is all the same. But now if you want to actually make this more routable, so here you're still kind of limited to a very, the routing is limited to a number of nodes. And then here you can become much more flexible in RoCE v2, where we actually replace this global routing header with IP and UDP. And the top layers we still keep. So, and how does this actually compare to something like TCP/IP, which we all know? So in TCP/IP, we just have regular Ethernet, we have IP and TCP, and the difference between essentially these two protocols is that in TCP/IP, the reliability and the flow control is all handled in the TCP layer. While here, we delegate the flow control to the fabric, and the fabric is at the same time almost lossless, and we only have to care about reliability in the upper layer. So, and to get actually this right, in this example now we see kind of how this looks like on the wire. So for instance, we have a requester which sends like a write command, which has like this space transport header, and then it has an additional header, which is called the extended transport header. And the space transport header has something like an opcode, which in this case is a write. And it has like an identifier for the queue pair. So this is similar to like a socket number. And it has a packet sequence number. And since this is a write, we also need a virtual address to know where to place the data and the length of this DMA request. And if this packet is successfully received, then the responder will actually reply with an acknowledgement. So again, we have the space transport header. Now the opcode will be an acknowledgement. We again specify this queue pair number, but they don't have to be the same because they're actually relative to the receiver. Even though they belong to the same queue pair, these numbers might vary because we send in the different direction. And then now this packet sequence number here will actually acknowledge that packet that you previously received. So this is very similar to what you have in something like TCP. However, there we use sequence numbers on bytes, and here we have sequence numbers on packet base. Okay. So with that, I would like to go to the next part where we look at the programmable NIC, which is implemented based on FPGA. And first, just an overview of the architecture. So we have an FPGA which has like a 10G Ethernet interface, and then directly we have connected a RoCE stack which implements RoCE v2. So we have IPv4 and UDP, and we have some helper modules for ping and address resolution. And then to address the host memory, we have to translate from virtual addresses, which are specified in the RDMA packets, to physical addresses, which are required to do transfers over PCIe. So we implement the TLB on the FPGA. And what we can introduce now on this programmable NIC is essentially processing in network on this RDMA data stream. So we have one stream when we receive data and one stream when we transmit data. And then on the host side, we implemented a driver which can actually configure this card, and it can issue commands and populate the TLB and so on. And of course, here you will run then your application. So now the RoCE stack itself is obviously we pipeline everything. So packet processing is pipelines, and we have like for each protocol or protocol header, we have a module that actually parses this header and extracts the required information. And then since this is stateful, so we have to keep track of these packet sequence numbers and so on, we have like these data structures in the center, which are mostly implemented as tables, and there we keep all the state. And we clearly separate this to simplify design and also have no direct influence between the two data types. And this design can support like thousands of queue pairs, in other words, connections. And currently it operates at 10G, since that's what we have on this board. Then now we're going to look in more detail how we actually do this packet processing. So essentially, as I said, we always parse the header, extract the metadata that is actually interesting to us and required further up in the stack. And then we remove that header and we align the packet. And I try to show you a little bit how this actually looks like in HLS, so high-level synthesis, or C++ like. Essentially, we have every cycle 8 bytes data that comes in. So every cycle we get a new word of data. And this is here, so we essentially have a stream where the packet comes in, and we can check if there is new data. If there's new data, we read it into this variable called current word. And then we have an object that's called header, which defines this IP4 header. And then this object will essentially parse this new data and into this header object. And once we completely parse the header, this flag is ready, is set. And we now know that all the following words are actually not header words anymore. They contain payload or headers for the following protocols. So these these words are essentially forwarded. And at the same time, we also write out this metadata that we extracted. So in this case, for instance, the source address and the length of the packet. And then once we consume the whole packet, we get this last flag here, and then just we reset this header object and also some other flags. So that's how this can be implemented in HLS. And as you have seen, each packet has this packet sequence number, and we have to keep track of it and like update the state. So here we have like a simplified version how we do this. Again, we would like parse the header in a module, and then this actually extracts the metadata as we have shown in the previous slide. And now we feed this into a state machine. And what the state machine does, it will get the queue pair number, which is like the unique identifier for that queue pair, and a request from this state table here, what is the expected packet sequence number. So this is, we receive data in order, and if we like the packet is lost, then these sequence numbers will not match anymore. So essentially there's 4 steps. First, we request this from the state table, then we get this data back, and then in the third step, we actually check if it matches or not. In case it matches, everything is fine, and we can issue an update where we update this packet sequence number, which you will expect next time. And we also indicate to this module here on the top if the payload or the rest of the packet should be forwarded or dropped. So if the packet is out of order and or in other ways not valid, essentially it could be corrupted sequence number or something, then we would just discard it. And in HLS, we essentially implement this state machine here with 2 states. So in the first state, we get like metadata in from the previous module, which parsed the header. we will use this metadata to request from the state table these expected sequence numbers. And then we go to the second state. We essentially wait for this expected sequence number to come back from the state table. And once we have it, we can compare what we expect with what was in the packet. And in case this matches, we will update it. Usually you just increment the sequence number, and we will tell this dropper module to not drop the data, and otherwise it will drop the data. So this is very simplified. That's more or less how this is done in hardware, and this ping pong takes around, so the request and response around 2 to 3 cycles, and then the update another 1 or 2 cycles. Okay. So then for the TLB, as you've seen, we actually have virtual addresses in the RDMA packet, so we have to translate from virtual to physical addresses. And we implemented TLB with 16,000 entries, and we operate on huge pages, which are 2 megabytes each. So this means we can support up to 32 gigabytes, or the programmable NIC can address up to 32 gigabytes of host memory, and this could actually be configured. So if we want to use more on-chip memory, we can even increase the number of entries in the TLB. And one thing we also have to handle is that while in the virtual space, all these pages are contiguous, in the physical space, they might not be, as you see here. And if we have a read or write which goes across 2 pages, for instance, here from the red into this orange page, then we have to essentially split that command in 2 parts so that we only read here from the red one and then here from the orange, and not that we read into unknown physical space. And this is also handled in, on the NIC. And then the memory management was, to actually get it working, was quite complicated. So essentially, we want to really have like 32 gigabytes, and since this has to be accessible by the NIC, we have to pin that memory. And this is very hard to do on the fly, since pages are allocated and deallocated. If we want to allocate a large chunk on the fly, this might actually not be available, and the operating system might not be able to give us this large region. So what we do now is essentially we tell the operating system to reserve this memory at boot time. So in our case, it will reserve 32 gigabytes of huge pages at boot time and expose them as a file in our, for instance, like huge pages. This could be the file. And then we have also a kernel driver, which we expose as def RoCE. And this kernel driver exposes like a memory mapped interface to then control the card. And then when the application starts, it essentially maps both this huge page file and that device into its own memory space. And then it can make a call to our kernel driver to hand over all these 2 megabyte pages, and the kernel driver will then pin them, so they will be always available, accessible from over DMA, and it will also give the mapping to physical addresses. So, and this is then needed to populate the TLB on the FPGA. And once we have done this, all this memory space is only allocated at boot time, so we don't do new allocations at runtime, and therefore essentially the application has to manage the whole space itself. And then once we have done all of this, we can initialize the card and start running the application. Okay. So now I want to give you like a few numbers, how this actually performs. So this is just the RoCE stack, and we implemented one-sided operations, read and write. And we're gonna, and this was implemented on this alpha data card. And this, we plugged it into 2 Xeon servers, which are actually dual socket, but we only use 1 socket. And they have up to 256 gigabytes of main memory, so 120 per socket. And we compare it to a Mellanox Connect X3 card, which is like a commercial card you can buy. And this card could actually do up to 56G, but to have like a more close comparison, we configured it to 8G SDR, which is the closest to the 10G Ethernet we have. on our implementation. So first we can look at the latency. In red we have this commercial Mellanox card, and in blue we have our programmable NIC, and then we have on the left always the write, and on the right the read. And we increased the payload size from 64 bytes to 4 kilobytes.
So the red is you, or the red is Mellanox?
No, the red is Mellanox.
The red is Mellanox, the blue is the FPGA.
Yeah.
The pale are write, and the saturated ones are read.
Exactly. So, and we see that the Mellanox card has a latency as low as around 2 microseconds, and then, yeah, with increasing payload like 1 or 2 kilobytes. Essentially here, this all fits in one packet, and at some point you need more than one packet on the wire, then it will increase. And we are for writes around 5.5 microseconds, and for reads around 8. And yeah, I mean, given that we implemented this on FPGA and we competed with an ASIC, I think this is very reasonable. We are like within 2 to 3x of the commercial solution. And the applications we're going to accelerate, you will see later on, they're mostly throughput oriented. So the raw latency has less of an impact. And with that, we can look at the throughput. Again, red is the Mellanox card, and the FPGA is blue. And these two dashed lines indicate like the theoretical output. So that's the throughput without including the headers. And we increase again the payload size from 1 kilobyte up to 1 gigabyte. And we see that with increasing payload, both the commercial card but also the FPGA get close to this theoretical limit. Yeah. And obviously, one thing with FPGA is always everything we implement requires resources, which means there's less space for other things. In our case, we want to do this processing in network. So the question is, how much resources are we using to implement the RoCE stack and so on? So this is a Vertex 7. And you see, for the logic resources, we use around 10%. And DRAM, which is essentially on-chip memory, we use around 8%. And this Vertex 7 is like a 2-generation-old device. So I also ported this on like the latest device generation. So that will be like an UltraScale Plus. That's what we have in the Ancient machine. And there we see that I think in general it has 2 to 3x more resources. And here the usage goes down by a factor of 2, roughly. So we will get even more resources for our application if we go to newer generation devices. So with that, I would like to go to the third part where we look at the use case, which is the distributed radix hash join. And first, I want to introduce how it actually works. So essentially, the distributed radix hash join has 4 phases. And in the first phase, or let's say, take a step back. So essentially, every database join tries to join 2 relations or database tables. And that's what we're going to do here in a distributed manner. So first, essentially, we compute histograms over the data, and we exchange these histograms in the first step. Then once this is done in the second step, we partition these relations by the number of, in our case, by the number of nodes, and we distribute it according to the histogram. So after the second phase, each node has the data that it needs in the third phase and in the final phase. So this network partition is essentially redistributing of data similar to like a shuffle in big data frameworks. And then in the third phase, we want to make these partitions as small as possible so they fit like in the L1 cache of the CPU, which will accelerate the fourth phase where we do like random lookups to compare these 2 partitions from the inner and the outer relation. So of course, we also do these 3 phases for the outer relation, and then, as I said, in the fourth phase, we have like partitions for the outer and the inner relation, and ideally they fit into the L1 cache, and then we can do the build and probe very efficiently. And generally, the partitioning is a dominating or a large part of the execution time in the hash join, which also makes sense because the partitioning actually will make sure that the build and probe becomes very fast. So, and what our goal is with the programmable NIC to actually offload this network partitioning phase and this local partitioning phase into the network card. And what we still do on the CPU, we'll do this build and probe, and of course the histogram to set up the NICs and so on. So how can we do this? Essentially, we can implement local and partitioning and the network partitioning module on the NIC, and we can extend the RDMA stack with a new command, which we call RDMA part. And it's more or less similar to an RDMA write, but instead of directly writing the receiving data into host memory, we feed it into our local partitioning module. We will partition the data and also buffer it, and then write the partitions to the corresponding memory locations. And these memory locations are essentially defined by the histogram. So the histogram that we compute in the first phase can be used to configure these modules on the NIC. So I will quickly show you like how these partitions work. So first, the network partition is quite simple because we only partition by the number of nodes. And in our case, we support up to 4 of them. So we have like these 3 parts. First, we partition the data. And then for each partition, essentially, we have a FIFO. And the reason for why we buffer is that we cannot send out single tuples. So on the network, essentially, you have like a maximum packet size, or MTU, maximum transfer unit. And we want to maximize this to reduce the overhead due to packet headers and so on. So in Ethernet, this is like 1500 bytes. So here we will like accumulate tuples until we reach this MTU, and then we will flush it out and send it over the network. And this mapping module essentially knows which partition has to go to which node. So it just keeps like a table with this mapping. That's pretty straightforward. Then the local partitioner is more complicated because now we want to support 1024 partitions, and this means this much higher fan out means actually that we have much more random writes to the memory. And since we are attached to our PCI, these random writes don't perform well. And what we have to do is essentially, again, buffer data similar before we buffered for the network to reduce the overhead. Now we buffer so we get better bandwidth over the PCI bus. And actually buffer in 2 stages. So the goal is to buffer up to 4 kilobytes. And to do that on the FPGA, we cannot use the on-chip memory. So we have to use the onboard DDR. So these ports have DDR memory. And but we also have random writes to this DDR memory, obviously, since we partition. So to reduce the impact of these random writes, we actually have write combiners on the on-chip memory. So we first buffer up to 16 tuples in FPGA on-chip memory. Then we flush these 16 tuples to DDR. And once here we have up to 4 kilobytes, we flush this over PCI. And as I had to figure out, one DDR could actually not handle line rate, so I even used both channels. And we split the data by the least significant bit between these 2 paths. Yeah. And this is hopefully something I think in the future might go away if we go past PCI. So for instance, in NCM, we will have a different interface, or I think many accelerators will get interfaces which provide you much better latency, and then also this random access should perform better, and you don't have to do as much buffering as here. So now I hope you more or less digested all this information, and with that we can look at how this actually performs. So first we have kind of micro benchmarks of this new command, the partitioning command, and if you look at the latency, you can see that mostly by introducing all this buffering logic, and we have to go to the onboard DDR, the latency gets significantly increased. So from around 5 to 8 microseconds. So this is all FPGA now. We get like close to 40. While this looks very severe here, actually in our use case, we are throughput oriented, and you will actually see that in the overall execution time, this latency difference doesn't really have an impact. Then if we look at the throughput, which is what actually matters to us, we can see again that this latency actually has some impact. So it takes more payload to actually get to this high bandwidth or close to the theoretical peak. So we really need like around 64 or 128 megabytes to get there. While this was much, the curve was much steeper with just read and write. Yeah. And then finally, we actually run this whole distributed radix join. As a baseline, we have like an implementation from Claude using RDMA over Infiniband fabric. So again, we configured this to use 8G SDR. And then we have just a RoCE implementation without offloading. This is partitioning. So essentially, these two do the same. The only difference is that here we have a slightly higher output. So here we have 8G SDR, here we have 10G Ethernet. And then the third one, we actually offload the network and local partitioning phase. And as a result, the network, the local partitioning phase is absorbed by the network partitioning and does not occur in these bars here. And you can see that between Infiniband and RoCE, of course, we have a slight improvement due to the different fabric, but then we have another improvement in when we offload because, as I said, this red part for the local partitioning completely disappears. In general, we are mostly network bound, as you can see. We are operating at 10G, and the network partitioning consumes most of the time. And then here, for the very large data, so here we have around 32 gigabytes of input and also correspondingly output data. We actually have some NUMA effects, which may slow down the build and probe phase for when we offload the partitioning. But otherwise, what you can see here is that for this large data, the two network phases, so the right one includes essentially the local partitioning, has only very marginal increase. So this additional work that we put on the NIC has almost no impact on the execution time.
Can you articulate on the NUMA effects? What's actually happening there?
Yeah, I mean, I'm not, it's very hard to say. I'm not completely clear about all the details, but essentially what we do is we reserve like these 32 gigabytes, right? And since it's done at boot time, I'm also not sure to which NUMA core these physical pages are actually assigned. And then we allocate also memory at runtime through the OS allocator. And I think at some point we just run out of memory on the socket where we run the join, and then some of the data will be on the other socket. Yes.
So in this diagram, you are comparing 8G to 10G, right?
Yes.
If you scale this blue phase by minus 20%, essentially, then how does it look like? Is RoCE actually better? Or not? Because it looks like, for example, for this 120.
I think it's slightly less. What I want to say.
The execution time will go up for Infiniband.
No, it should go down, right?
Yeah, it should go down.
It should actually be 10G.
Yes.
I mean, you are comparing an artificially slow network to.
So the RoCE and the Infiniband should look identical, right?
Exactly. So basically, the blue bars should be identical in all.
Yes, in theory. I mean, the headers are actually. You've seen not here, but if you look at the output, it's not essentially exactly 20%. So this is like 9.47,
sure.
And this is something like 7.9.
Sure.
So, and
but once you account for that, you would expect RoCE and Infiniband to look the same. Once you
Exactly.
scale for the actual achievable throughput,
It should be the same.
they should look the same.
I mean,
So
I
basically,
ran
it
this
would be
number.
nice to just reorder the bars in this diagram, right, in this stack, so that you have the blue thing on top, and then we can compare basically red and whatever brown.
Yeah.
In order diagrams.
Yeah.
But now I cannot compare this. So for me now, eyeballing it, it looks like it's exactly the same. Like if I combine this red and brown, and the brown and the RoCE with offload.
Offloading is
The
absorbed.
offloading is still beating RoCE.
So the
It's clearly
offloading
wrong,
gives
right?
clearly a benefit because this is the same network. What you mean from here to here? Essentially, these loops should be the same. If
Yeah,
you would like
exactly.
reorder it, you would actually see if the red and the brown is the same.
Yeah, exactly. This
Yeah.
is what I would like to see. But
That's
now
yeah, that's a good suggestion. I mean, in an earlier version, actually, I kind of did this back on the envelope, and then it was not the same. So Infiniband was still faster if adjusted, but I think this improved. So that was in the early version of the driver, I had much more overhead. So yeah, in the latest driver, the driver is very efficient regarding the latency. So I'm not sure. Yeah, I think I should do it and see, or I can essentially
just reorder.
reorder the stack.
Okay, one question, why you need a new one when you two CPU? Maybe just one is better.
Yeah, I agree. So this is just the machines I had available. Ideally, if I only have one socket, I cannot run into this kind of issue. That's correct.
Maybe you can just use one. You can manually control.
But it is going to come up, right? The issue with NUMIC is going to come up eventually. Right? You can't hide from it forever.
No, so it's
I mean,
might not common like somehow.
I mean, in servers, it's common.
Plenty of
You
two-socket machines in the world.
generally have two sockets, and then it also matters like where your NIC is actually. Usually, the NIC is attached to one socket,
Yeah.
so then it really matters where you run your application. You can also introduce more latency and so on. Yeah, it's not that obvious what actually happens. So yeah, I hope I will find out more about exactly what happens. Okay.
Just to understand, so you artificially throttle the throughput of the Infiniband, right?
Yes.
Does it have any influence on the latency?
Yes. So not for very small payload, but of course for larger payloads. So I did like in this latency where I compared just the latency of read and write commands. If you increase the payload, then with higher bandwidth, you get also lower latency because yeah, you fit more per cycle.
Packet transmission times
Yeah.
are affected, but the underlying latency is not. First byte,
Yeah.
first line.
That's correct, but I wait until I receive
Yeah,
the
first
last
byte,
byte.
last byte obviously slows down because
Yeah.
the packet transmission times are now long.
So here so you first do the network partition and then you do the hash job, like do that prop. How about overlapping? So basically you just receive the data and then just do that prop at the same time. Okay, so the object here is okay. Network cannot fully utilize the memory bandwidth, right? Then actually you can use the CPU to access the memory at the same time.
Yeah, I mean, one reason for this is really that we are also essentially at 10G and like Claude run this join on like QDR and so on, which is much faster, right? So then this reload.
Slower than the memory bandwidth.
I mean, it's approaching, but yeah, currently it's still slower. But I mean, what is overlapped? So in the case without offloading, doing this network partitioning, you also partition the data and issuing data transfer. That's overlapped. This happens at the same time. You're not partitioning everything and then send it. You like start while you partition, you issue send.
So, I mean, maybe you can just do the simple hash job, don't do the partitional hash job.
And then
I guess should be faster. Because you can overlap the network and the computation.
But it's already over.
It is overlapped. In the network partitioning phase, this is overlapped. As I said, you go through the data and you partition, and whenever, essentially it's similar to what I do in hardware, whenever you have like a MTU or like some chunk of data, you send it. So then sending and
I think you have an
partitioning.
interesting offline discussion.
Yeah. Okay. So apart from like the improvement we get through offloading, one thing that's also the case, we actually reduce, free up resources on the CPU. So what we use here is 8 cores. That's the number of cores on the machine or on one socket. And this is used for both the network and local partitioning. But when we offload these two phases, actually we don't use any CPU cores. We only use them in the final phase here in the build-up probe again. But in the actual partitioning phase, the CPU is not involved. Yeah, so with that, I'm already at the end. I think time is also up. So essentially, one thing I mentioned, this is still running at 10G. However, in data centers and so on, 40 or 50G is now the state of the art, and this will only increase. So what I'm trying to do is essentially push the bandwidth, clock up the frequency, and potentially increase the width of the data path. And of course, we can now, since we have the RDMA stack, we can introduce further commands. But we have to figure out what are use cases that actually make sense. And one thing I want to look into is essentially in MPI, you have like data types, and you might want to restructure data before you send it, but now you could do this on the fly. You could also like do transformations of the data. And while this can be done in MPI, this also maps somehow to databases where we have like columns or rows, and we could on the fly reformat or restructure this data. And one thing I'm looking at currently is like in Portals, there's something like matching. As you saw now in RDMA, we have addresses, and in matching, essentially you send more like a bit code. And then on the receiving side, you have like a list that matches bit code to addresses, and the receiver can essentially populate this list, and not the sender has to define the address. So it's like an indirection. And yeah, this will be open source. Since it's currently under submission, I'm waiting for the results. And then we will open source the RoCE stack and the driver and everything that is needed to run this. And yeah, that's it.
So your TLB is really, really big. Do you have any feeling for how much it's costing you in latency? Like where your latency budget is being spent? And how much this TLB is costing you?
No, the TLB is like, it's one table.
Yeah.
And it's the lookup is one cycle, right?
You've got one cycle lookup into the table.
It's very simplified TLB.
Yeah. Okay.
I also have only one virtual space. I don't support. Yeah.
So you might want to look at perhaps using the IO and IO menu. Right? Because if you stick this thing behind an IO menu, then that IO menu can potentially do the translations for you.
Yeah.
Right, and then you can take that to the output. We can take that.
Yeah. Okay.